Hey everyone, in this video we are going to review for the Unit 1 exam, which covers number systems and order of operations. So the first question we have is just writing the symbols for each of our special sets. So in here you're going to go in, you may have these memorized already. If not, you need to go back and review your notes and find all the special symbols for our special sets. Alright, so I've just written down our first one. The natural numbers is the N with the extra line in it. I'll give you a couple more. The integers are the Z with the extra line in it. And the real numbers are an R with an extra line. Alright, so go through your notes, find all those symbols, make sure you either have those memorized or write those on your formula sheet. Alright, so speaking of the formula sheet, you can come by my office if you would like me to get a piece of paper for you, but your formula sheet is essentially just a half sheet of plain copy paper, printer paper, whatever. If you prefer lined paper, if you just want to use your notebook paper, that's fine. And you can write whatever you want on both sides. So you can write on both sides. So take 1/2 sheet of copy paper or lined notebook paper, whatever you prefer, and then you can write on both sides of that. Whatever you want. I'm not taking these up, so feel free to write whatever you want on there. Whoops, I don't know why I wrote write on both papers. I meant to write on both sides. Sorry. You can write on both sides.
I'll scramble on.
Alright, the next question we have is identical to something that we've seen in our notes, just with different values over here in the left-hand column. Alright, so we are just identifying the sets to which each of the following numbers belongs by marking an X in the appropriate boxes. Alright, so remember your little funnel chart. Remember your little funnel chart, which says, down here at the bottom, we've got all of the real numbers. Sorry. We've got all of the real numbers. On the left, we've got this funnel of just the irrational numbers. Irrational numbers. And then on the right, at the very top, we've got our natural numbers. I'm just going to write the symbol. Natural numbers. That funnels into the whole numbers. That funnels into the integers. And that funnels into the rationals. The rationals funnel into the reals. Okay, so whenever you look at a number, so for example, let's say we're looking at the number -2/3, you're going to determine, okay, which set am I identifying that number belongs in? I know that that is an integer over an integer, over an integer. So I know it's a rational number. So I'm putting it in the rational number funnel, and it's going to funnel down into the real numbers. Okay. All right. So this is a rational, and it's also a real. All right. So it's a rational number, and it's also a real number. All right, so I want you to go through your notes and repeat this process for every other number. For our next example, we have 7. All right, so we have 7. 7 is a natural number. It's one of our counting numbers. So that we drop it into the natural number funnel. It goes into the naturals, the whole numbers, the integers, the rationals, and the reals. All right, and so you're going to repeat that process. Now, I did just want to remind you about this last row in the table. This number 2 divided by 0 is undefined. We're not allowed to divide by 0. So I just wanted to have this one as an example of something that is not natural, not whole, not an integer, not a rational number, not an irrational number, or real. Right, so just an example of something that's none of those things. Right, so next we have write 4 examples of rational numbers and 4 examples of irrational numbers. Right, so many answers are possible here. I just want to give you some ideas. For the rational numbers, remember that the definition of a rational number is numbers that can be written as an integer divided by an integer. And then our little cheat sheet or our little hint for ourselves is that the terminating decimals and the repeating decimals are also rational numbers. And irrational numbers are just the opposite of rational numbers. So these are numbers that cannot be written as an integer divided by an integer. And they are non-terminating decimals, meaning they go on forever. They do not end. And they're non-repeating, so they have no patterns that can be identified. All right, so many answers possible there, but that should give you some direction. All right, next we have our funnel diagram, and I'm asking you to explain the diagram in your own words. So just to give you some direction here, explain this, give me a few sentences, 2 to 4 sentences. You know, imagine that you were explaining to a classmate that missed class that day how to use this funnel diagram. All right, so just give me a few sentences explaining how you can use this diagram, why it is helpful, and why are the funnels set up the way they are. Is the order of the funnels important? So just a few sentences about that. All right, so next we have give 2 examples of rational numbers that are not integers. All right, so 2 examples of rational numbers that are not integers. So remember, if you were looking at that funnel diagram, the funnel diagram, this is just a chunk of it, just one little piece. But we had the integers here, and the integers flow down into the rationals. So every integer, let's see, if you imagine these like a marble, that's kind of how I imagine them. If you imagine your number as this little marble that I'm dropping into the integer funnel, so say -7, it flows down through the integer funnel and into the rational funnel. So -7 is an integer, but it's also a rational number. So I want you to give me what are some things that are rational numbers that do not get put into the integer funnel. So one example would be 1/2. All right, so 1/2 is an integer over an integer. But if you're looking at the whole number, or the entire number, I should say, 1/2 is not an integer, but it is a rational number. All right, and then next, give me 2 examples of integers that are not whole numbers. All right, so once again, we're looking at our little funnel diagram, and we have the whole numbers, which flow into the integers. All right, so give me some examples of numbers that would fall into the integer funnel, but do not belong in the whole number funnel. So I'm thinking like -700. That's not a whole number, but it is an integer. All right, next we have, is 2/3 times 31/5 a rational number? All right, so let's see. 2/3 times 31/5. Well, when we multiply fractions, we just multiply the numerators and then multiply the denominators. All right, so we're going to multiply the numerators, multiply the denominators. Let's see. I know the denominator, 3 times 5 is 15. I'll have to grab my calculator. Oh, no, I don't. That's just multiplied by 2. All right, so if you do 31 doubled, that would be 62. All right, so is 62/15 a rational number? Absolutely. It's an integer over an integer. So, yes, 62/15 is a rational number. All right, and then just sort of generalizing that last problem, do you think that a rational number times a rational number is always a rational number? Explain your answer. All right, so just to give you some guidance on this one, think about that a rational number times a rational number. You could rewrite that as an integer of an integer times an integer over an integer. So what do you think is going to happen when you multiply an integer times an integer? So think about what an integer is. It's a positive or a negative whole number as well as 0. Right, so in the set of integers are positive and negative whole numbers. As well as 0. Do you think that an integer times an integer is always going to give you back an integer? So do you think that this is true? Is an integer times an integer always going to give you an integer? Yes, absolutely. So an integer times an integer is always going to result in an integer, and then same for the denominator. Integer times integer is always an integer, and that means that the result is always going to be a rational number. But feel free to reword that however you want. I wanted to go over a couple of the order of operations problems. So it says evaluate each expression using the order of operations. Okay, so we have the absolute value of 2 times 3 minus 7 times 4. So I'm going to just really exaggerate these absolute value bars so you can tell that those are absolute values and not, ones. So if you write them too small, they can look like ones. And then it might look like 12 times 3 minus 7 times 4. All right, so make sure you really exaggerate those absolute values so you can tell what is what. All right, so whether you want to use PEMDAS or GEMS is totally up to you, whichever way you prefer to think about it. I'm going to use PEMDAS just because that's what I'm most comfortable with. So I'm going to start by doing my grouping. I'm thinking of an absolute value here as a grouping, so I'm just going to do everything inside the absolute value first. There's actually nothing outside of the absolute value in this expression, so I don't have to worry about that. But I'm going to start, or I'm going to proceed by doing my multiplication, and I'm doing that left to right, so I'm going to do 2 times 3, and then I'm going to come over here and do 7 times 4. All right, so that's equal to, long straight line, 2 times 3 is 6, minus 7 times 4 is 28. All right, then I'm subtracting. Again, I'm working inside of the absolute values here. 6 minus 28 would be negative 22. And the absolute value of negative 22 would be 22. All right, so remember, absolute values, absolute value makes things positive. If it is already positive, it's not going to do anything to it. So for example, if you have like absolute value of 5, that's just 5. Right, so the absolute value is defined as the distance that a number is from 0. So it's always positive. Distance is always positive. All right, on this next one, I just wanted to remind you that when you have an expression in the numerator, say something being subtracted or something being added, something being multiplied within the numerator of a denominator of a fraction, then you want, sorry, I accidentally paused that. You want to imagine that there are little invisible parentheses around the numerator and the denominator. All right, so just remember that if you have a fraction and it's got some operation, some expression in the numerator or in the denominator, you're going to imagine that there are little parentheses around those, which is going to tell us to do those first, right? So that's our grouping symbol or our parentheses if you're thinking about GEMS or PEMDAS. And then I wanted to throw this one in here just to remind you how to do this one. Here, I'm thinking of the radical as kind of our grouping symbol, so I'm working inside of the radical first. And then I'm going to start by just squaring both of those numbers. That's my exponent, so that would be my second step of my order of operations. So 39 squared is 1521, and 36 squared is 1296. Then if you subtract those, Again, I'm working inside of my little grouping symbol here, my radical. So I am just following along with the order of operations, trying to simplify inside of this grouping symbol. So now I'm subtracting those. 1521 minus 1296 is 225, and the square root of 225 is 15. All right, then we have one of these. If you remember, we did these in class together, or you guys chose a problem to do, and you did that on the board, sorry. And it said to place parentheses if needed to make each of the following equations true. So I just picked number 10 part C to do with you guys. So we have 5 plus 4 plus 9 divided by 3 equals 6. All right, so you'll have to kind of, guess and check here. So you might want to start by saying, okay, what if I have this in parentheses? Then that would be 5 plus 4 plus, this will be 3. 5 plus 4 is 9, plus 3 will be 12. So that's definitely not right. Right, then you might think, okay, well, maybe I need to group these. All right, so 4 plus 9 is 13. All right, that would give me 5 plus 13 divided by 3. All right, that's definitely not going to work, right? 13 divided by 3 is not a whole number. All right, and then you can try to group all 3 of those. 5 plus 4 plus 9 is 18. 18 divided by 3 is 6. All right, so that's right. And then we have in each of the following, tell what computation must be done last according to the order of operations. All right, so some of you did one of these on the board the other day. In this example, you can either actually work out the problem, or if you just want to do it in your head and think of what computation you would do last, that's fine too. I think I just worked out the problem. So we've got 5 times 6 minus 3 times 4 plus 2. All right, so I'm going to start by doing my multiplication. 5 times 6 is 30. 3 times 4 is 12. So we have 30 minus 12 plus 2. So the computation that must be done last would be addition. All right, so the computation that must be done last would be addition, since subtraction and addition are completed left to right. And then the last question, explain what PEMDAS means and what GEMS means as it relates to the order of operations. Which one do you think you would use in your classroom and why? Right, so of course we know that PEMDAS is parentheses, exponents, multiplication, division, addition, subtraction. GEMS is grouping, exponents, multiplication, division, subtraction, and addition. And then just give me a couple of sentences about which one do you think you would use in your classroom and why. All right, guys, that's everything for the exam review. I do want to just take a couple of seconds and tell you about the exam. There'll be a mix of problems. There'll be some like show your work, problems, maybe a matching, and then there'll be some open-ended questions like we've seen here, explaining your reasoning behind things. I would say max number of questions would be 20. Probably going to see less than that though. So maximum number of questions is 20, probably less, and then you will, you can leave after the exam is over. So once you're done, you can leave. And oh, don't forget, homework is due on, or excuse me, I should say due by 11:59 p.m. on exam day. All right, so whatever day, the day we take the exam, your homework will be due that night by 11:59 p.m. All right, guys, if you have any more questions, oh, and you can use calculators, but I will ask you specifically, there'll be directions on there to show your work on many of the problems. So feel free to use the calculator to check your answer, but I will want to see the work shown if you want to get the full credit. All right, so if you have any additional questions, please let me know. Otherwise, I'll see you guys soon.